Well, welcome everybody to tonight's meeting of the Astronomical Society of Edinburgh. I'll just be giving one or two updates and then we'll get on to the substance of tonight's meeting, which is a talk by Lynn Smith on the solar cycle. Ahead of us starting that, if you have any questions, as members know on Zoom, if you put them in the chat room, and Peter will call you at the end to ask. If you're joining us on YouTube, then please put any questions in the comments section, and we will try and pick a few of those out as time permits, and we'll ask them. Okay, so just to bring people up to speed, members will have heard already of the sad passing of Ron Livesey at the age of 91. Ron was the director of the Aurora section of the BAA for a long time, and at the funeral, Will told the tale of Ron's homemade jam magnetometer, and that we provided a link to the service, so you're able to look at that. And I was somewhat surprised when it wasn't a jam jar; it was actually a Nescafe jar. In fact, there is Ron's jam magnetometer. Now I know it's a lot easier to use your app and know when the Aurora is busy, but if you fancied making one, the construction details are available on our website. And for anybody who wants to stay in touch with us, you can do it in a variety of ways. Our website contains lots of information. You can follow us on Facebook, on Twitter, and all the talks we've given on YouTube are available on our YouTube channel. And just a note about what's coming up in the near future. On the 5th of March, we have Skyrora, the local rocket company. I think they're about 2 or 3 miles from my house. And their director of launch is going to give us a talk. And that will be followed by our YouTube star, Alan Pickup, who will be giving his summary of the March sky. On the 10th, it's a members meeting, imaging and observing group. And on the 19th of March, a slight change in the way that the normal technical information we get out in these meetings. It's Literature and Astronomy by Randall Stevenson. Bruce is going to give us a historical view on the 16th of April from the Venus tablets of Amisaduga, which sounds fascinating. And then we've got 2 more classic talks, the technical talks. One, the Outer Solar System Origins Survey by Dr. Sam Lawyer, and The Dark Side of the Universe by Professor Catherine Hymans from Edinburgh University. So that's what's to look forward to. But tonight, I'm going to hand over to Lynn, if you'd like to share your slides, Lynn.
Okay.
I'll stop sharing.
That's it, thank you. Right, that's it. Can you see that okay?
Yeah.
Yes.
Good, thank you. Right, okay.
No,
good evening.
No, it's just your eclipses.
Oh, right, okay. Let's start again then. Right, just bear with me a second. We did it before. Can you see it now?
Nope.
Oh, right. What's going on at the moment?
We know it worked because we've tried it.
That's strange, isn't it? Right. Don't know what's going on then. Share that. That's it. I think I've got it this time.
Yep. That's it.
That's it, thank goodness. Whew. Right, well, after those many false starts, good evening, and thank you very much for your invite for me to talk to Edinburgh Astronomical Society once more. Just pity I can't do it in person, but anyway, those are the times we're in. So this evening, I'd like to have a chat about the solar cycle And it's a particularly good time to be looking at the solar cycle, as we're just coming to the end of one and the start of another. So a great time to look at the sun. So tonight we're going to have a look at the solar history of the solar cycle. We're going to look back at the high points of cycle 24, the one that's just ending. And then we'll look at the new one and see, well, what were the first signs of the new cycle and how can we tell new cycle spots from the old ones? And then look forward and see, well, what might we expect of this new cycle? Now, being astronomers, of course, you'll all be wanting huge, big telescopes because you know that the large aperture is what you need to try and capture light from these very, very faint objects way out in space. But with solar astronomy, of course, it's the opposite. We've got a relatively near object and it's far too bright, really. So small telescopes are ideal, which is good if you're just setting out in astronomy and you haven't got a huge budget or you don't want to invest a fortune to start off with. Then obviously lunar and solar astronomy are great starting points. But even then, we've still got to use solar filters or project the solar image through a telescope onto a piece of white card to see it. And obviously, you will know never ever to look through an unprotected telescope at the sun, particularly if you're doing public outreach. You want to be very, very careful that no one can approach a telescope and have a wee squint through before you put that solar filter on, because they will if they can. This is my setup. I've got a Celestron next star here, and it's got a full aperture type 2 solar filter over the objective end. And this is the hydrogen alpha telescope. So it's a narrowband telescope and it's looking at the red end of the spectrum at the hydrogen alpha line. So for white light, we're looking at the solar photosphere. So basically that's looking at sunspots, faculae. And then we're looking at the chromosphere, which is the atmosphere of the sun. And then we're looking for filaments and prominences, plage, and hopefully a flare or two. So a close-up of the white light telescope, just to show you the solar filter. It's a glass solar filter, which gives you a nice pleasing kind of yellow sun, which is fine, but you can use mylar or barda film, which gives you a kind of silvery sun, and that's a film that you can make your own filter out of. You get exactly the same result. It's just the same quality, but barda film or mylar is an awful lot cheaper if you've got a little bit of DIY skill to make your own filter. So, I mean, that would cost them about a touch with prices, £100 or so, depending on the aperture, whereas you can pick up a sheet of barda film an awful lot cheaper than that. And of course, that will make several filters as well, which is another bonus. And so that's what I see. I mean, it's obviously it is Soho, but it's not very far off what I actually see when I look through the telescope. I prefer direct viewing, probably because getting a bit older these days, my eyesight isn't what it was. And if you project the solar image, I find you just do not see the sunspots as clearly. And particularly if you're looking for minor sunspots like this one on here, it's probably, well, arguable for to see that anyway with direct vision. So small. Yesterday we had a very small sunspot just up there. It lasted a day or so before it faded. And now this morning we have this one here. You can barely see it. It's a test of your eyesight, but there it is. It's typical really for solar minimum. What we have had is southern hemisphere activity of the new cycle, and we're just starting with the north now, and that's why we're seeing such small groups, whereas in the southern ones are really getting to be quite developed, as we'll see a little bit later on. So there's the H alpha. You can buy it's a filter as a telescope itself, so you don't need to put anything additional onto that. You can look straight through it. It's perfectly safe. Or you can buy a similar equipment to fit onto your own refractor, which would have a front end part and then a rear end part here. It would be similar to that at the back blocking filter at the observational end. There's nothing really to choose between the two types. They're both about as expensive as each other, although prices have been coming down a little bit in recent years. I think that one was a couple of thousand, something like that, but I've had it at least 20 years now. So if you think of an instrument, you know, lasting you 20 odd years, then the money isn't really that much. And I don't think they're really that much more expensive today. So comparatively, they have come down a lot in price, particularly I think with Lunt coming on the market. And I've heard some pretty good reports about them. And that's what I see looking through the H alpha telescope. So a nice sort of pleasing red sun. looking at the solar atmosphere, the chromosphere. Usually my vision is a little bit sharper than that, I must admit. That's a little bit blurred. Seeing couldn't have been so good on the day that was taken. But you will see we've got a sunspot here. You can't see the sunspots as well, but you wouldn't expect to. That's not the point, because you're looking at the layer over the top of the photosphere, over the top of the sunspot, and you're looking at the magnetic disturbance that the sunspot is creating in the chromosphere. And so that's what you will see. So you can see some little brighter areas, plage, dark area here, filament, more filaments here, and I think it's a tiny prominence out there. And all these is plasma that is suspended on a magnetic field line, and it's shown as an emission feature when it's seen at the limb, and it's shown here as an absorption feature when it's seen over the brighter disk of the sun. So this is a filament, and this is a prominence, but it's exactly the same feature, just seen at different locations on the sun. This is the equipment of another member of the solar section, and he has got piggyback H-alpha scope on there, rather nice refractor, and he's also got a CCD camera linked to his covered laptop so he can do some solar imaging. So what about the solar cycle then? Well, what is it? Well, you can see on this graph the last 4 solar cycles. So this is the one that's just ending here, 24. And the previous 3. And straight away, you can notice there is a little bit of a difference. So we've had a very quiet cycle this time. So we've had 3 quite good activity cycles leading on from the late 70s. And this recent one, which has just ended, was quite low. So goodness knows what's going to happen with the next one. It's anyone's guess, really. Chinese astronomers were started looking at the sun. We've got records going back there for about 800 BC. Presumably they were noting down naked eye sunspots that we were seeing in the sun when it was perhaps in a fog bank or something like that. So they were the first really to note down that there was imperfections on the sun. There were these large black holes, as they thought they were. Of course, we know now that they're not holes at all, they're magnetic areas, just choking down on the rising heat from inside the or energy from inside the sun's interior. Thomas Harriot, around about 1610, when the telescope was first invented, was the first one to turn it on the sun. I hope he did projection and didn't look through it, because they didn't have solar filters in those days. I think they used coloured glass. I'm not quite sure what his eyesight ended up like. But anyway, there we are. He was the first guy to officially have a look through at the sun and note the sunspots. And to see they weren't just there as naked eye objects, but were there all the time, more or less. Samuel Schwab, 1843, had a bit of a project, because Mercury's orbit wasn't really conforming to Darwin principles. So he reckoned that something was tugging on it, and that had to be a little planet between the sun and Mercury. So he set himself down to observe every single speck that might cross the solar disk to try and find this planet. So he spent a good 10 years or so doing that. He didn't ever find, of course, what wasn't there, because there isn't such a planet. But he did discover something quite unusual about all these sunspots. They seem to ebb and flow over this sort of 10-year period. And then this got the interest of Robert Wolf going, and he did his own observations, and he started to look back over the work of astronomers back as far as records went for 100 years or so. And he was able to determine that, in fact, sunspots did ebb and flow over around about an 11-year period, and he started to note that down. So he tracked it back to, I think it was 1745, the first observations, and he established the first solar minimum, that occurred 1755. And then it rose to a maximum, and then back to a minimum in 1766. And this is where we get cycle 24 and cycle 25 from, because Wolf established the first one way back in 1755, and roughly every 11 years thereafter, we've had a solar cycle. So we're now on 25. Interesting enough to look at this and see, well, the first 2 sort of shortest solar cycles of 9 and 9 1/4 years occurred really early on in Mr. Wolf's log. And also interesting, the longest, and 2 other very long ones appeared there. I'm not sure whether that was just because of the data, I don't know. But interestingly enough, that all the other solar cycles from then to now have been quite boringly 10 to 11 years or so. So we haven't had that variation. Now here we have a diagram back again, but I've also added in what's called a butterfly diagram onto it. And that just shows you the appearance of the sunspots as they start with the new cycle, start at high latitude, and then they work their way down towards the solar equator on both hemispheres to the solar equator up here. But you'll also notice that as they get to be old spots, we get the new cycle spots starting at high latitude before the old spots disappear. So we've got a period of about 18 months to 2 years where we have both old cycle spots at low latitude and new cycle spots starting at high latitude, both existing on the sun at the same time. And this is more or less where we are with this new cycle here. We're just getting to the point where the old cycle spots have died out. I say died out, or dying out. I haven't seen one for a while, so maybe one will pop up tomorrow, just prove me wrong. But they seem to have stopped, and we're just now getting the new cycle spots emerging. Interestingly enough, the new cycle spots tend to pop up a little bit higher in latitude once the old cycle spots die down. And that's something we're looking for, haven't yet found, because they've not been particularly high, the new cycle spots. They're only up to about sort of 35, maybe 40, but nothing higher than that. Sunspots can appear up to about 60, 70 degrees, but that's pretty unusual, and they only get a handful of those doing so. Most of them tend to occur from around about 5 to 7 degrees up to about 35, maybe 40 degrees. That's north or south, that's the norm. So the new cycle ones, then they tend to appear a little bit lower. They're about 25 to 30, and then once the old cycle spots die out, they'll pop up a little bit higher to about 35 or so. And that's the situation where we are now. And of course, over the period of the next few years, they will gradually wind their way back down to the solar equator and end up down there at solar minimum. It's not... We never see sunspots at the poles, never appear that high, and it's unusual to find them actually on the equator, although never say never, because I have actually observed sunspots who've crossed the equator. Pretty rare, but it has happened. So we have magnetic polarity of sunspots, as you know, is the dual polarity in the sunspot. You can see this is a satellite picture, a magnetometer, and in the northern hemisphere, and this particular picture anyway, we have a negative polarity followed by positive polarity. And in the southern hemisphere, it's exactly the opposite. It's positive followed by negative. So when the old cycle stops, new cycle spots flip around, and you will then get in the northern hemisphere positive followed by negative, and in the south, of course, it's the opposite is true. And this will lead some people to say, well, your solar cycle isn't actually 11 years long, but it's 22 years. Well, that's correct. To get right back down to the original magnetic configuration of the sun, yes, it does take approximately 22 years, but it's usual for us to refer to a solar cycle as 11 years. But that's how you can tell whether it's a new cycle sunspot or an old, because they will display different polarity within the same hemisphere. So looking back then, you're probably quite familiar with this sort of a chart. If we go back, we can see we have a Maunder maximum here, and then the solar cycles kind of decrease a little bit, rise again, and then go down to this period of the Dalton minimum, where we had a couple of very low intensity cycles, then back up again, and then of course the rather famous Maunder minimum, which lasted about 70 years, from 1745 to 1715. It was about, in that 70-year period, they had as many sunspots over that 70 years as we would experience within 1 year of our modern age. So that must be a pretty miserable time to be a solar observer, I must admit. We can go back even further and look at carbon dating. So back to our Maunder minimum here, and then go back even further. So we can see rises, we can see troughs, but there doesn't seem to be any actual sort of pattern to it at all. We can only say there is a variation in solar output. So peaks and troughs are normal, but very difficult to foretell something, how high something will go or how low something will go. We just don't know. But here's the modern maximum. So you can see that we have been through a period of quite high intensity. So it would be normal, really. You'd think perhaps we're going to reach a period where it's not going to be quite so high. But the sun likes to surprise us, so we'll have to wait and see. Now, although we've had a very low intensity cycle, cycle 24 has produced some real stunning highlights, and I'd just like to share a few with you. So if we go back to 2011, and solar maximum for this last cycle was in 2012 and 2014. And that's normal. You get a peak in one hemisphere, and then you get a peak in the next hemisphere. So there we have a sunspot group. It's an E-type class. We have A to F classifications for sunspots, and an A-type group would be very tiny. You can probably just see something there, a single pore like that would be an A-type class group. This would be B class because you've got it's extended, it's more than just a few degrees, but there's no penumbra around any of those sunspots. This one, well, it's a single penumbra, so actually an H class, and this would be a D class because it's bipolar, 2 penumbral sunspots, perhaps a few bits and pieces in between, and it doesn't extend more than 10 degrees in latitude. But then this big spot round here, we're going up in classification to E. So we've got it's bipolar, I've got at least 2 major spots, probably 3 major spots in that one. But its longitude will be in excess of 10 degrees, but not exceeding 15. So that gives us E classification. And if it's highly complex like that one is, but it exceeds 15 degrees in longitude, and then it'll be the top group of F class. So that's how it's sorted out. We get other things in the feature like EKO that just describes the type of penumbra around the main leading spot, or the type of classification of the spot itself, whether it's open, whether it's intermediate with lots of pores in between, or if it be C class, then it would have lots of different penumbral spots in between the leader and the follower. So once you know the key to the code, it's quite easy to describe a sunspot in these terms. And if you ever read any of my reports in the BEA Solar Section newsletter, it's full of codes like that. So moving on, and the following day, it did extend. It was more than 15 degrees in longitude. So it became an F-type group, and it was measured in 16th of millions of solar hemisphere. You can find out how to do that just by feeding in your drawing, or better your image, into a number of programs you can find online, and that will calculate that sort of area for you. And there we can see it progresses. It was easily seen with the PNE, that's protected naked eye. To do that, you just simply take your solar filter off your telescope and hold it up to the sun and just look through it naked eye. And if you can see a sunspot, then note that in your observing log as seen with a protected naked eye. So 3 main components in this: nice leader, cluster there of followers, and then all this stuff back here. Now, because it's dual polarity, there will be a neutral line running through there where the polarity changes, probably through here. And that's always an area to watch, because where you get the neutral line, you're getting lots of disconnection and reconnection of magnetic field lines, and that's where you're likely to see solar flares occurring. So that's a close-up of this particular spot. Not particularly clear, this one, but you can see what we call the light bridge across there. So when you've got the dark umbra, you've got the fainter penumbra around it, then these filaments, are not to be confused with H-alpha filaments in any way, but sunspot filaments there would start to grow across the main penumbra, and that's always a sign that the group is in some sort of decay, because the field strength is declining. It can, of course, strengthen again, and the sunspot can consolidate and grow, but generally is a sign that it's weakening, and the sign that the sunspot is probably going to decay. Now, this image was taken in calcium K-line, which is also part of the lower corona. It's just a bit lower than what you've taken H-alpha, and it photographs very well towards the blue end of the spectrum, and that's the calcium K-line. And this gives you the plage. That's where you're really looking at calcium plage. And you're seeing really the magnetic influence of these sunspots in plage. So you're seeing the chromospheric network that overlies the entire solar disk, and this intense area here around the sunspot, and other active areas that haven't yet emerged in white light but certainly have emerged in plage. And this is the same group here in H alpha. So you see, we don't have an awful lot of H alpha plage, doesn't show it up that well. But we have got some minor flares just in there as well. So you can see rather a nice filament down there. One or two others, but I don't think we've got any prominences on show on that one. We get to the 8th of the month, then it lay across the central meridian. And it had started more or less to consolidate really into 2 components as opposed to 3. And again, it's this area here that you can just see. That's where the neutral line is. And look at all that sort of growth in there. And that's give you an indicator to watch for that in H alpha and see if you can get any flaring activity. So we've just moved on to July in 2012. We can see we had another one quite decent, rounded the limb there, AR 1520, and that was preceded by a lot of faculae. And faculae is a white light feature. It's a strong magnetic area, but it's obviously not as strong as an active region or a sunspot area. It was 1100 millionths, also a type F group, so quite substantial. And as it progressed, and if you can see, that was a couple of days worth, it just flicked from one to the other there. You can see that spot in the lead there, and there's the group we're looking at. There's that spot again. And look how it's extended there. It's really grown. Probably show that as a separate group. For BAA purposes anyway, if you take the center of that group to the center of that group, and it's more than 10 degrees in longitude, then it would count it for BAA purposes as separate groups. This doesn't always hold true for NOAA or the Space Weather Prediction Center, who set up the active region number. It was the Americans around about 1972 that decided they would assign every active region a number, and that's what we're using here. They don't quite work to the same principles as the BAA, so sometimes they might classify that as just one group. So when that rolls on or develops onto the disk, it doesn't have an active region number, which can be a bit of a shame because they reckon it's all one. So we tend to refer that to AR 1520A, AR 1520B if it came to dividing it. And by the way, that numbers are not longer than that. Just for brevity, we use the last 4 letters, 4 numbers of the digit. Now, this is a fabulous image here, back to July 09, with Damien Peach turned his talents onto the sun and came up with a superb image like that. I mean, to think that's taken basically by an amateur, even for one of the best amateurs on the planet, it's absolutely fabulous. So we have here, we can see clearly the dark umbra and the penumbra and the penumbral filaments there. And these are really just stretched out granules. It's the magnetic field stretching all this granulation out into this fantastic convoluted state. Here you can see the actual granulation beautifully outlined here. And what this is, it's rising packets of elevator shafts, however you want to think of it, of plasma from the interior of the sun that's rising up to the photosphere, where light is then let loose. Light is released, energy is released, and then that cools some of the plasma, which then gets darker as it gets cooler, and then it goes back down into the interior of the sun, down what we call these intergranular lanes. That's what gives the granulation that kind of mottled effect. So deep down in the sun, we have kinks in the magnetic field that form, and these are called flux tubes. And when these flux tubes emerge out onto the photosphere, they do so as bright points of light. And in H alpha, we would look on that as being plage, H alpha plage. But on the photosphere, they're also bright points of light. When they're strong enough, they get together and they grow. And if they do manage to grow magnetically in strength, then they become darker. And as they become darker, because they're choking off that rising energy from the interior of the sun, and so that's what's forming and becomes cooler. That's what's forming a sunspot, and that's all it is. That's what a sunspot actually is. This is the massive sunspot that we're looking at from Damien Peach, and we're looking at it now by an image from Dave Tyler, and of course it's in hydrogen alpha. So we're looking over the top of that sunspot through the atmosphere to all the magnetic activity going on. So we can see here we have these little jets. There's lots and lots of jets in H alpha all over the sun. These are called spicules. And the magnetic configuration of the whole active region there is stretching out some of these spicules and stretching them into longer fibrils, or what we call fibrils. And they're just enlarged spicules, they're darker. But when you look through a H alpha telescope, you'll see the magnetic configuration of a sunspot group on the sun. And that's what you're looking at. You're looking at these enhanced and stretched spicules called fibrils that curl and twist and that magnetic configuration. So in here, you can see we've also got some rather nice filaments and of course some brighter areas of some minor flare activity going on. Back to white light and back to Damien, a day or two later, you can see that we've got some more light bridges forming over the sunspot, so a bit more of a sign of decay. And this was taken by Dave Tyler just before that sunspot rotated around the western limb. And you can see we've still got some really nice filaments associated with it, and plenty of plage and bright flaring material in here. And incidentally, there we have some little bright lights in there, and they're probably element bombs or mini flares. So not quite full flare, but all the same, little bright dots, which tend to occur either around the edges of sunspots or, as in this case, at the base of a rather nice filament, which that is there. So this was also seen by the protected naked eye pretty much throughout its passage between the 11th and the 15th of July. And of course, it released quite a few decent flares along the way. Had to show you this as well. This was a fantastic prominence, really extensive, which was in September of 2012. So you can see there, this is all this plasma caught up here in this magnetic field, and it just not quite enough strength for it to reach the escape velocity of the sun, and it's just starting to fall back down here. And the same on this side, it's starting to loop across into this other prominence here. So a really interesting feature. For later on that day, Soho coronagraph also captured this. I'm not sure if it was related to that same prominence that Dave captured in the morning, though I would suspect so. Then you can see the release of material here and this huge bubble of plasma that's been ejected from the sun in a coronal mass ejection. Just moving on here, in October, we have a fabulous video by Andy Devey. Andy used to live in South Yorkshire, and he got so fed up with the cloudy days of the UK that he decided, right, I'm off to Spain. So that's where he is now, happily doing B&B and solar observing. So that's what I call dedication to duty. So he's captured here a really lovely movie. Obviously, it's speeded up a good deal, of an X-class flare. That's something I haven't actually seen myself. Seen quite a few M-class, C-class, and all the rest of it, but not an X-class. This again is an American classification. I think they did this for the GOES satellite. So they have A, B, and C class flares, then it jumps to M class, and then it jumps to X class, being the highest. Each category has subcategories of 1 to 9. So you could get M1 to M9, and then it would go X, then X1, and X is open-ended, so that can go as high as it as you like, depending on how bad it is, really. But you can see how powerful that is. Magnificent. I think we have another one here from Andy as well, showing an M-class flare, and I put this one in because you can see there that material there being ejected, but it doesn't quite gain escape velocity, and it gets pulled back down into the sun. But look at the rivers there, the ribbons there of the flare. So it doesn't just happen as sort of a big explosive event, but it can actually run through the entire active area in ribbon flares like that. So that was an M-class flare. Right, going on to January 2014, we had this one come around, 1944, seen by the limb, and it looked quite spectacular. Only E-class at this time, but it had certainly potential. You can see as it rotated on, then we've got a lot more stuff here. And this, as I was saying earlier, is the interesting bit. Let's just move on a wee bit. So it's extending there. We have, obviously, that would be naked eye, possibly that one too, but certainly that one, and a lot of trailing material. So where you've got a lot of these detached umbra here, and some tiny pores, that's the area where that neutral line will lie, and that's where you've got the reconnection going on, I would think, of magnetic fields, and that's going to be the active area. That's where in H alpha you're going to see the flares, and indeed there we are. That's the H alpha picture a day or so later, so you can see this is really quite benign, but look at all that following region. So there's lots going on there, lots of flares on that really bright area, and look at all these rather nice filaments as well. Not reasonable prominences around the edge there. So you can see it's typical solar maximum type image where you've got really superbly dominant feature here, flaring going on, lots of dark filaments and a fair range of prominences as well. So it crossed the central meridian, it reached 1580 millions and some 19 degrees in length. So that was a pretty decent length of a sunspot. So you're really one of the longest I've seen, really fantastic. I mean, when you turn the telescope on that, it's an absolute wow moment, beautiful. Here it is in H alpha, and again you can see lots of flare activity going on in the center, lots of really nice filaments in there as well, and of course you can see those stretched spicules called fibrils there, so you can see the magnetic configuration all around that sunspot too. And there it is, just about to go over the limb. It was naked eye, not only just one spot in it, but 2 spots. That's quite unusual to get 2 naked eye spots in one active area. So that was quite spectacular. So they were recorded on the 6th, 7th, 8th and 9th as well. It won't have faded on the 8th. I just didn't have an observation on that day to record. But here we have the active area, and here you can see evidence that a filament and prominence is the same feature. It starts off here as a dark feature, and then it rises up over the limb as a prominence. And look at this beautiful feature here. So a really nice filament, like a big, huge smoking chimney. And in your mind, if you transpose that to the limb, that would be a fabulous prominence. It would look absolutely spectacular. It's a pretty good sunspot because it survived another rotation and it got renumbered. So 1944 became 1967. And unusually, it grew around the back of the sun. So when it re-emerged again, it was actually larger than it was before. Normally, they tend to fade a little bit. So that was quite unusual that it actually grew and became back larger than before, which was great. Really enjoyed that. So you can see again, you've got huge sunspot leading, substantial sunspot in the middle, lots and lots of material behind. And in H alpha, again, you can see you've got lovely filaments, and you've got in that trailing part there, that's where the action was. So you've got your flares going on as well. This was taken by Peter Pace. Sadly, we lost Peter last year, but his images in calcium K-line were particularly good. So you can see that sunspot group, and you can see the amount of influence of that sunspot, which covers about 25% of the sun. Absolutely fantastic. Even this one up here was, it's quite substantial to say the least. So a cracking image there of a calcium plage accompanying that sunspot. It did in fact come round for a 3rd rotation, and it got renumbered again, but it was a shadow of its former self. And so that was it there, just a single unipolar sunspot. And the final one I'd like to show you this evening is my favourite, so I'm saving the best to last. And here it is, absolutely huge, 170,000 kilometres from north to south. It came round in October 2014. And normally in white light, you can't see the magnetic configuration of a sunspot, but I'm saying to you, you can. I mean, look at it. It's so twisted in white light. I mean, you just know in H alpha, that's going to be something really special. It's just such an absolute mess. It's like it's just like a solar hurricane that's on there. It's just sort of, you can't sort of make sense of it at all, which is great news. Right, what's it going to look like in H alpha? Well, it looked pretty good. So here we are. We can see the lead sunspot there, lots of light bridges there, and look at all this sort of mess here. Neutral line be somewhere about down there. Lots of stuff trailing as well here, so that's going to be lots of action in H alpha. This is a white light feature. This is not a flare. So this is a white light feature called an umbral dot, and these occur on the periphery of the umbra and penumbra. Really better for images. I've never seen one through observation. That my eyesight isn't what it used to be, but you never know. If you've got really good eyesight, you might. But for images, it's something to look for. And what you're seeing here is an opaqueness. You're looking through the layers into the hotter layers down within the solar interior itself. So it's quite common, actually, especially around solar maximum. So look out for those. And again, note in your log. So we can see that sunspot now in 3 lights. In white light, just to show the huge extent over the solar surface. Calcium K line there, when we see the plage. And in H alpha on this occasion, it was particularly quiet at that moment in time, but it didn't stay that way. Also look, really nice filament in the northern hemisphere. So here we have it lashing off one of its many X-class flares, which was nicely captured by Dave Tyler towards the end of October. And it released an awful lot. I mean, M-class flares were 10 a penny, and X-class flares were getting that way. As you can see down here, it's unusual for a sunspot to release quite so many X-class flares, flying away one after the other. And how I didn't actually manage to view one, I don't know. But anyway, there we go. So you can see down here, October the 27th was a busy day, 6.7, an X 6.7. That is a pretty decent flare by any means at all. So fabulous sunspot, didn't let us down. And there we have it, just disappearing off the western limb. And it was, of course, visible to protect a naked eye. You would expect it to be, with 2,280 millionths as it crossed the limb. So what do we know then? What have we found out? Well, we do know that despite cycle 24 being the weakest cycle since cycle 14, which was the early part of the 1900s, it still produced some remarkable active regions. And we also know that generally the sunspots, the active regions in cycle 24, were smaller than all of those other cycles. And we know that only cycle 23 failed to produce a larger one than that solar hurricane that we're looking at. But on average, all the same, their sunspots were larger than those of cycle 24. So we had a low activity cycle, and we had basically quite weak active regions. So it was the weakest for 100 years. On average, all our sunspot groups were smaller in millions of square hemisphere. And personal observations in H alpha showed very little activity during this minimum. During the 23 to 24 cycle minimum, yeah, it was quite low and extended and really boring, but there was quite a lot of H alpha activity going on. This time, it's not been like that. There have been days and days and days where there's been nothing to record, nothing happening in H alpha at all. And that has been really quite unusual. So little comparison between cycle 23 and 24. You can see for the 3 years of minimum, they were low, they were extended. This has probably been a bit deeper, as you can see, 61 to 77% as opposed to 42 and 73, but probably not quite as low. As you can see in 2020, it was heading really low to begin with, and then it really cracked off. So it's been only 57% spotless there. So it's been a little bit deeper than the last one, but that was extended more than this one. I thought I was going to lose the will to live during that one. I must admit, it was pretty grim, but this one hasn't been too bad. Nothing compared, of course, to the famous cycle of 1913, where the minimum there was just dragged on, 311 spotless days. I mean, you wouldn't even bother getting the telescope out after a while, would you? So how did we know that cycle 25 had started? Well, we had no visible sunspot, but we did have a magnetic disturbance. So we know what that is now, and that appeared 3 years ago now, almost anyway. We have the central meridian down here. We say that it's 0. So south 31, west 14. So it'll be 14 degrees west of that central meridian. So at 10, 15-ish there. And then 31, so 10, 20, 30, somewhere around about here it emerged. And that was the start of it. So it was really a heads up that cycle 25 is going to start, because until you get the first sunspot, it hasn't officially started. And we had to wait a while. It took us about a year before the actual sunspot did emerge. So we've seen then the first sunspots of the new cycle, they come about 18 months before the current cycle ends. And we've seen they appear around about latitude 25 to 30, and then they move up to 30, maybe 35, after the old cycle spots fade. So there, a year later, in July the 6th, 2019, hallelujah, we had our first visible sunspot of the new cycle. So again, it was a southern hemisphere sunspot, just slightly east of the meridian, so somewhere probably down to about where that D is. And there it was in all its glory, in white light and in H alpha. Nothing much to shout about, I must admit, but it was very, very significant. The new solar cycle had now started. Captured also in calcium K line, so they have a bit of calcium plage with it. You can just about see the sunspot. And we had to wait then some considerable time. We obviously had a lot of sunspots, but they were the old cycle spots, until Christmas. And then we got another one. And so you can see this was at South 29, pretty much where you'd expect it to be. And again, it's a BXO type sunspot, so no penumbra, just a couple of sunspots going along. But there we are. That was the second one. And there we have it in H alpha, and then it really can see that magnetic configuration there etched out by those extended fibrils. Now this one occurred on April the 1st, and it wasn't an April Fool. It was the very first northern sunspot. There's not been many of those to date, so it was really significant, and it appeared at north 28 degrees. So again, not a lot to look at, but significant in its own little way. And in H alpha, again, you can see that magnetic disturbance and a little bit of plage just in there as well. So that was it. We knew we had the cycle really started. Both hemispheres had fired up. So we know that all the new sunspots coexist together. The old sunspots, they'll be near the equator, and the new ones will be up around about 25 to 30. And we've seen that they have been. And then we had this happened in April this year. So, and this has happened quite a few times since. So we have an old cycle spot there, South 7, where you expect it to be at low latitude. And then we have a new cycle spot with reverse polarity. And there it is, sitting also fairly low latitude at South 17. It should be up here somewhere. So why is that happening? Don't know. But it has happened again quite a few times. So it's just a bit odd. So of the new cycle, we've had our first M-class flare as well. This was taken by stereo A, and the Earth side facing is here, so this would be the limb as far as we were concerned. So this was behind the limb, we couldn't see it, and we waited with bated breath for this fabulous active area to rotate, and when it came over it just about faded and gone away, so that was a big disappointment. But anyway, in due course, in June, we had this one, and this is a southern hemisphere spot. And the reason why this is significant is because it was the first one that actually had a penumbra around it. So it's starting to mature. So you can see there, it's not quite full, but on the next slide, you can see it is. So it did progress as it rotated across the disk, CSO type group, and the first, as I say, substantial sunspot of the new solar cycle. We also started getting some quite decent prominences, as you can see this one from July, and it lasted the following day and even extended. It was huge on the 31st, but then unfortunately it lifted and we didn't see it thereafter. So coming up to October, and again, we've got another substantial sunspot here. And this, although it doesn't look particularly much, it was significant because it survived a complete transit across the disk from east to west. These are all signs that the solar cycle is starting to get going. And this did. And there's another low latitude one, look, it's only South 14. So again, a little bit strange. So looking at an H alpha, there's nothing really much going on there, but I'd like to draw your attention to this rather nice prominence sitting up there on the northeast limb, which was imaged by Carl Bowron, with a rather nice image of that super prominence. Now, this one was really the first sort of substantial sunspot of the new cycle. It formed mid-disk, and I'll just play you a little sequence as it goes across. You can see now it's rapidly expanded overnight, and it's still growing. And look what happens the next day. It splits in two. There's nothing happening in the middle. And then this forms rapidly overnight. And just watch that again. Just see how it's rapid growth. And you think, yeah, this is going to really be something. And then it suddenly fades off. But then this happens. And this was really active and actually released a very nice flare. So in November, we had another one, which turned out to be the largest one of the cycle so far. So we're certainly stepping up step by step. And again, this survived a full transit. So I just play this through. As you can see, this is more like what you expect at solar maximum. It's a really nice sunspot developing as it goes. So here's a close-up of it in night, and here we have it in H alpha. And you can just see in there, we have some tiny flares called element bombs in there. And coming into November, now we had a really large spot. That's not the one we've just seen, by the way, that's another one. But it's these I like to draw your attention to. This one looked quite benign, but it wasn't. And this was just huge. I couldn't believe it. This so early in the solar cycle, we've got such a massive sunspot coming around, easily seen with the protected naked eye. So it's a fabulous image of it here from Philippe Tozé over in France. And there it is, fabulous. And that's the other wee one there, just preceding it. And there's a flare coming out of the first sunspot. So that small benign looking one wasn't quite as benign as it looked. And there's that large follower coming around. So I'll just play the sequence as it progressed on a little bit more. That's it after a day or so, fully onto the disk. You can just see there's some other little spots trailing around behind. And again, you've got lots of faculae accompanying these spots. In H alpha, plenty going on there as well. And there it is. So you can see there, you can see the faculae. You obviously faculae far better nearer the limb because you've got sort of less atmosphere to look through. So there's a better contrast. And you can just see there that there's some growing followers happening there. And they start to grow the following day. And just down in there, we get something appearing as well. Your nice H alpha, so that shows you obviously there's some nice plage with it, and there's a rather nice filament which was significant with that sunspot for a couple of days. And there it is, it just starts to grow in there. So there's another sunspot forming as it progresses, starting to split up a bit here as well. So you think, well, perhaps it's going to fade. It had a bit of a kidney sort of bean shape to it, but then it reformed again the following day. And this is still a growing area. This is still growing as well, but then it reconfigures and consolidates again. And then that one just faded away. So it didn't come to very much at all. And then the followers also started to fade away as well. There is some calcium K lines. You can see how the extent of it all there. And there's that little leader. And then on to December. So we're nearly up to time. We had another couple of decent sunspot groups came round. A rather nice picture from Brian Halls there and the close-up of them. And in calcium K line showing you the extent of the plage. Christmas Day, of course, was spent at the telescope, good for Michael, and quite a few others were doing the same thing. This was an interesting sunspot. And I can just sort of play it. There it is there. If you just sort of watch that, this kind of disappears a bit. As we go through, that starts to dissipate. And this turns, it starts off. So this one here, sorry, it was this one I'm talking about. This starts off as a north-south configured sunspot consisting of two small penumbral spots. I'm not saying that never happens, it does. You do see it occasionally, but just watch the progress of this one as it goes across. It starts to turn, look at that. Turns from north-south to an east-west configuration, and that is quite unusual. So this has been the norm. This is what we've been looking at. I'm so glad that Sherry and Carl took this picture, because imagers always like to take a picture of something, but Sherry took a picture of nothing, which I really thank her for, because it's very difficult to show someone just how boring the sun can be on occasions, but that's how it's been during solar minimum. Nothing in white light or H alpha or anything else, and just record 0. So what will 25 look like when it's starting to get going? How is it going to go? Well, deep down in the sun, we have these solar conveyor belts, and they sort of define what the sunspots are going to be like way into the future with this meridional flow. So it's deep down in the sun. We have solar seismology that's kind of really come to the fore in sort of the last 10 years or so. Scientists are able to tell what lies deep within the sun through this technique. We know that this solar conveyor belt evolves the magnetic field from this very sort of complex movements that are deep down in the sun. So we have a base flow going down towards the equator. There's a different belt in each hemisphere. And that moves at a different rate, moves at a different rate to the one that's going upward. We've also been able to tell that we've got the slowing down of these conveyor belts. So it's decelerated. Now it's about the slowest on record. And they're also out of sync because we've got the southern flow is now slower than the northern flow. And scientists also are able to measure the magnetic field within the umbra of sunspots, and they've been finding out that those have been decreasing quite steadily. Now, they've worked out that if it gets below 1500 Gauss, then there won't be enough energy within the sunspot area or a magnetic area to form a sunspot at all. We'll cross that line in 2022, and I'm not saying whether that is going to happen, and I would say that it probably isn't, but we'll need to wait and see. It sounded a long way off, 2022, when I first started talking about this, but it's not so far away now. So cycle 25 could fade away next year, so we'll have to wait and observe and find out, and it could go down to Dalton minimum levels. Personally, I don't think we're going to see that. But just to finish with, there are two recent studies that have come out. One is of the termination event, and that's at the end of the 22-year magnetic cycle that we looked at. And that suggests that transition of the magnetism to at the end of sort of magnetic cycle can be either slow or fast. Well, they've decided that this one has been fast, very fast, and that would be an indicator then of a very strong solar cycle. So on this work, we're expecting a stronger than average solar cycle to come. And one of their predictions is that sunspots should be higher than 40 degrees north and south. Well, we've seen that so far that has not happened until last weekend. You might have seen this on Space Weather. We had it didn't actually form a sunspot, but it tried very hard and it only just sort of missed it. So we have some plage fall here, and it formed at north 60 degrees. So it's only one incident, but that would seem to bear out what they're saying. So we'll see, is that going to happen more and more, or is it just a one-off? Don't know. It's pretty rare that you get sunspots as high as that. So it's a kind of wait and see at the moment. This is the stage we're in. So observations are certainly required over the next 12 months to 2 years to see what's going to occur. Now, I said there was two studies. There's another study of north and south sunspot asymmetry. And that, of course, this is being astronomy, suggests that cycle 25 will be about 25% to 40% weaker than cycle 24, and it will in fact be one of the weakest on record. Well, you couldn't get two works really further apart, could you? So we know that cycle 25 had started, and we know it could fade away. We could see an extremely high energy cycle, or perhaps one that's just a bit more energetic than 24, or we could see one that's very poor indeed. So I'll just finish by saying what will happen next. Well, in the words of Sir Patrick Moore, we simply don't know. And I think that sums it up beautifully, because the professionals haven't a clue either. So what we will do is we will stand by our telescopes, we'll observe, we'll record, and hopefully I'll come back in a few years and tell you what did happen. Thank you very much.
Thank you, Lynn. Perhaps people can unmute and thank Lynn. Excellent. It's good to get a handle on the classifications and the nomenclature. Any questions, Peter?
Yeah, I think Neil's first with his question. Neil, would you like to unmute and go ahead?
Yeah, thank you, Peter. That was fascinating. I didn't realise there was so much to it, and I've definitely got fear of missing out now, so I'm going to go off and get a filter. But my question is, given that the appearance of the spots change, so often, how can you tell it's the same spot after another rotation?
Yeah, good question. You work that out really by its coordinates, longitude and latitude. So it'll take about 27 days once it's rotated on the western limb to come back. Sorry, half of that, because that's a full rotation, is 27 days. So it's about 13 to 14 days later, it'll appear back on the eastern limb, and you just look for the timing and also its coordinates. It will drift a little bit in longitude, perhaps slightly in latitude as well, but not usually significantly. And NOAA is usually quite, or Space Weather Prediction Centre, as it likes to be known as now, it is quite helpful at informing you that it's a possible return. I always say possible return, you can never be absolutely sure that it is a return, but it is likely return of a certain sunspot if it's in the same location and roughly 13 to 14 days when you're expecting it to reappear over the limb.
Okay, thank you.
Thanks. Mark has a question.
Thank you, Lynn. That was really good. There's quite a few of us in society now trying to image sunspots. What sort of information would be useful to you in the BAA for tracking sunspots? What sort of observations are you looking for?
Really, I mean, we do this for pleasure, basically. So, I mean, you can obviously image whatever it is you want to image, whatever you enjoy imaging. I mean, that's what I do. I observe what I enjoy. There's certain parts of solar astronomy I don't do, imaging being one of them. And I don't do the radio side of it. I have another assistant director that helps me out in that. So you just do the bits that you enjoy doing. I'm looking obviously for active regions, nice movies, as you've seen. What really the kind of images you've seen tonight are always very welcome. But I'm not an imager myself, so I can't give you a lot of advice on that. But if you want to contact me by email, then I'll be very happy to give you the advice, because we've got loads of great images and they've all written some very good material to have in the section archive. So I provide the material for you, but I can't really give you any great tips because I'm just not an imager.
Yeah, thank you.
That's all the members one. Is there any more members' questions, please, before we move on?
One, Peter from Andrew.
Right.
Two small ones, please. Could you run me past again the issue of plage? And the picture you showed, it looked like a carpet we were looking down into, below the surface. Can you tell me again what that was, please?
Right, well, plage, I mean, that's bright patches or areas of enhanced temperature that's found mainly near to active regions, although plage can appear anywhere in sunspot latitudes, and they often herald the emergence of an active region, or they remain after it's decayed. Quite similar to that of faculae, really, in white light, although that relationship is not really fully understood. Plage contains emerging magnetic flux tubes and reconnecting field lines, which lead to a release of energy at higher temperatures, and that's why it's kind of bright and cloud-like. It often surrounds sunspot groups in that sort of cloud-like formation as the sunspot grows. And if it's bipolar, which most sunspots tend to be, then the plage divides between the leader and the follower sunspots along that neutral line I was talking about. And that's where polarity reverses. So when the sunspot decays, that neutral line also becomes blurred, and that eventually dissipates as well. Sorry, the second part to your question I didn't quite get, about carpet or something?
Yes, you looked in below the surface and said there were like columns rising up and they could combine and behave together.
Oh yeah, that's the granulation you're talking about in white light. Well, deep down in the convection zone, in obviously there's a radiative zone, there's the core, there's a radiative zone, and then there's a convection zone where plasma is churned around and then it's brought up to the surface in these great big convection cells, and that's where energy is then released from those cells on the surface, what we call the photosphere. That's where white light is released. But in that release of energy, then the plasma becomes cooler. And then it falls down the sort of sides of the big tube, if you like, and it looks darker, and that's why you get this sort of intergranular lanes. That's why it looks granulated, because you've got the bright rising plasma releasing energy and the cooler stuff going back down into the interior of the sun to be reheated and brought back up. So it's just constantly churning.
Thank you for a really super fluent presentation.
Thank you.
Thanks, Lynn. I have one. Has anybody made any correlation between sun cycles and climate variations?
Yeah, a question I always get asked. Basically, we don't know. Probably not. I've asked this question myself of solar physicists when I've had them come to talk to my own society. They say the variation in the solar cycle is not sufficient to affect the solar constant received at the top of Earth's atmosphere, that they would at all really make a significant change to us. However, there is some evidence that the ultraviolet light change could affect weather patterns such as El Nino. Don't ask me how, but that's what I'm told, that it could be weather pattern effect like that, but not really. Our variable star isn't that variable. It doesn't really make that difference to us. I mean, most people are trying to think about the Maunder Minimum when the Thames froze over and that kind of thing. But I understand that that only happened in the northern hemisphere and not in the south. So therefore, it would happen in both hemispheres. I think there was an eruption of a volcano somewhere in the northern hemisphere, and by that time it filled the atmosphere with a good deal of dust. So that could well have been the cause of those cold winters. And just coincidental, it happened to happen during the Maunder Minimum.
Okay, thank you for that. Mark, anything on YouTube?
I can.
Oh, sorry, Will, you're doing YouTube.
Yeah. Okay. Yeah. You've actually seemed to have just answered Basil T's question about the Maunder Minimum, which is pretty good. Just a general one, actually, from we go up from Rebecca Gonzalez. It may just be a very straightforward one, but how much light, is there a technical term for how much light the sun emits per day? Is it just like one solar day, or is there an official technical term? Does it vary?
I don't know that. I mean, we've got the solar constant. So that's about the nearest thing I can think of, is the amount of light received at top of Earth's atmosphere is the solar constant. I can't tell you what that would be in mathematical terms offhand. I'm not to my knowledge. I don't know any more than that, I'm afraid.
Oh, okay, that's marvelous. And just following on from Neil's question, I just wondered if there was a record for the length of a big sunspot, if it's managed to survive, say, more than 3 solar rotations or anything like that.
Yeah, a good question. I really don't know the answer to that one. It must be pretty rare, because that one we've seen tonight that survived 3 rotations, that's the first one that I can remember observing. I've been observing, I started observing in 1969 or thereabouts, but I did stop for about 25 years or something. Life took over, started again in the late 90s, and I've been observing ever since. And that's the only one that I've observed that's survived more than 2 rotations. So it's quite rare. But yeah, I don't know what the record is. That's something for me to look up.
Absolutely marvelous. Thank you.
Thank you.
Thank you.
I must apologize as well that you can't see me. It's a fault with my camera on my laptop. I've tried everything, but it just, well, it doesn't really matter, I suppose. But it's not that I'm hiding. It doesn't work.
Can I add one more? Can I add one more question from YouTube, which I think is interesting? Is how do you what was it again? How do you actually work out what the longitude of a sunspot is? I mean, there's not the same sort of markers that there are on Earth, but things change more on the sun. Yeah, there's a very complicated way of doing that, which you have to project the sun, and there's a number of aids that you can get to help you work that out. One of those aids being the BA Solar Handbook, so I'll give you a little plug for that. But yeah, you have to do projection basically, and then a little bit of maths to work it out. It's difficult to explain. I could show it to you, and I've done some workshops showing people how to do that. Always good to be able to do it. But in this day of the computer age, you don't need to do that. There are websites, again, Space Weather Prediction of NOAA, that will produce daily sunspots, giving the AR number. It gives you longitude, latitude. It gives you the category. I mean, talking about A, B, C, D, E, and F. It gives you the length of it in degrees. It gives you the whole works. So if anybody, it's very difficult to find, but I've got it. So if anybody wants to know it, just drop me an email and I'll send you the link to that Space Weather Prediction Center site.
site, and you can look it up. There's other things as well. Solar Ham, I think he's quite good as well. He produces a lot of that kind of information, which is a lot easier to find. And space weather, of course, that's a good one. Big Bear Observatory, that's another one that's got a lot of observing logs on it that gives you that kind of information. Just got to dig a little bit deep into the site, but you will find it. So there's lots of information online. You can find it if you just spend an hour or two hoofing around the internet with it, which is what I do.
Thanks for that, Lynn. There was Graham followed up with a question more or less in the same area. I don't see you on the screen, Graham. Did that answer cover what you're asking? Graham was saying he used to calculate. Yes, he's happy. But he used to calculate the latitudes with your BAA handbook.
That's right. Yeah. A solar disk behind it, and a little bit of calculation. Orientation of the disk is the key. If you get that properly orientated, you're laughing. And then just use the BA handbook just to work very simple arithmetic to work it out. Yeah, yeah. I used to love doing it. I don't do it now because I don't project. I'll look through it and then look it up on the internet. Everybody else.
Well,
And
thank you.
I'll ask one more thing here. Mick Nichols says, give us your prediction, Lynn. Is it worth buying any more solar observing and imaging kit?
Absolutely. Look, the sun is the kind of object that always surprises. Just when you think you've got it cracked, you know exactly how it's going to behave, it'll change its mind, it'll do something ridiculous. So it'll either die out altogether or it'll blow us all to pieces. I don't know, but it's going to be worth watching. Solar observing is the most exciting observing you can do in astronomy. It's something happening all the time. Even when at minimum, you know, it can still burst out a huge sunspot or something, or a flare or prominence, something to keep you going. And when it's solar maximum, I mean, it's just awesome. Awesome. I drag people off the street, whether they want to be dragged or not, to the telescope and say, look at this, you know, it's fantastic.
I
Yeah,
must admit, Lynn, that compared to standing outside when it's -3, I often think solar observing has a lot going for it.
correct. We're not fools.
And I'd like to remind members that the Society does have a couple of solar scopes, a Lunt and a Nexstar, which are available if they want to use them. And I think a few years ago when I was using it, there were some wonderful solar prominences visible through those. Can I get everybody to thank you once again, please, Lynn? Thank you very much indeed.
My pleasure. Thank you very much for inviting me.
Thank you.
Thank you.